So I'm Redden, co-founder and CTO of Blue River Technology. We're a company that builds big agriculture equipment. We started out building this bot, which we won't be able to see right now, but it went through. Yeah, I can't even go and do request access. But it went through and it had cameras, and it's pulled behind a tractor. It is in several forms 20 feet wide, but is now 60 feet wide and goes 6 miles an hour. And it has cameras that detect every individual plant. And then in less than 80 milliseconds, it processes the image, determines what's a weed and what's a crop. It then has a bank of actuators that go through and actuate and spray and kill just the weeds. And then it has a second camera system beyond then that takes images of how it acted, and continuously every 50 feet it collects several images and analyzes how it acted, and it adjusts for its own internal parameters, such as the spacing of the nozzles, and this makes sure that it maintains centimeter level accuracy as it goes 6 to 10 miles an hour and being 60 feet wide with hundreds of actuators, several dozen cameras on board, and maintains that accuracy as it goes through the field. We built a whole fleet, and it operated for some amount of time on around 10% of the lettuce in the United States. And now we're transferring that over. And one of the big things that happened to us was we went through, the company was started in 2011. And in 2011, there was only kind of the top way to do machine learning. And we started in lettuce thinning. And in about 2015 or so, we switched over to do deep learning, and that enabled us to do weeding. And one of the big differences here was that we knew in 2011 that the accuracy of the computer vision models wasn't good enough to do weeding applications. So we'd gone through and we had benchmarked and we had figured, and like the only reason to talk about any of the things that we're going to talk about, the only reason to do deep learning, the only reason to do any of these things is because you want your model to get to be more accurate. And so there's some threshold where if you're an entrepreneur, you're going to be deciding, can I start my business? Is this good enough to actually launch a product off of, or is it not? And for us, in 2011, when we came out, we found that the classical computer vision models were good enough to do one application, lettuce thinning, but were not good enough to do lettuce weeding. And so as time went on, yeah, so lettuce thinning is one where all of the same plant are in the field, and you have to differentiate in between individual plants that are all the same species. And weeding, you start to have a jumbled mess of many different types of plants throughout the field. And so in one case, you have a very regular pattern of plants. And you can depend on this, and you can depend on it being a certain size. In weeding applications, you start to get plants that vary in size much more drastically. They also vary in how they look much more drastically. And so as we came through and we were taking a look at this, we found that we really needed the more controlled area of thinning to actually start and launch the business into. And so I'd propose that one of the big shifts that has happened is this. And but I think that you can now go out and you can take new training data. So say we had a model, we were wanting a model to go and work in Texas, for example, and we hadn't been in hailstorm cotton before. And so we could go and we could collect data. We could have it labeled that had hail-damaged cotton. We could then put that into our training data, train the model on it, not do a bunch of model tweaks, not do new hyperparameter searches, not do any new engineering work there, and then on the other end, reliably expect a model to come out that would work on hail-damaged cotton. And so big question is, like, how true is that flow, right? It's not 0% true, and it's not 100% true. It's somewhere in there. Just like all of these models, they're not 0% accurate, they're not 100% accurate, they're somewhere in there in how accurate they are. And so, for me, a lot of this is about keying in on exactly what percent accurate you're at. You're taking step-by-step, you're doing step-by-step experiments over many months to figure out how to increase that accuracy, especially if you're looking at the entrepreneurship track where you need a model to get to be above a certain percent to make the whole business valid. Otherwise, if it's below a certain percent, the whole business is not valid. And so it's going to compare the journey a little bit to one that, who has seen the documentary? Okay, so I don't want to ruin anything, but he lives, and he soloed El Cap. And so if you're... So before deep learning, we were probably around 80% accurate on weeding, on that transfer over. We're in like the 90-some% on thinning. There was a lot less kind of penalty for not being accurate in the previous application, which really enabled it. Post deep learning, we strive in like the 90-95%, and then you can kind of make up some of ambiguous or bad decisions based on your action characteristics. That's a good question. And so how do you solo El Cap? Well, if you want to start soloing, you got to climb small mountains. You got to use gear. You should study the mountain in lots of detail from the ground. You should study the mountains and the routes when you're actually on the mountain, actually climbing. You should climb with a friend with gear. You should do this a lot. Then if you've done all those things and you feel very ready, you should consider free soloing El Cap. And so how do you train neural networks? You should train with small models. You should use visualizations. You should come back and you should study the data before you start training. You should study it in detail. You should study the data while you're training. You should train with lots of visualizations and the debugging. And when you're really sure, you can tune and squeeze, and you can do all these kind of final steps with the model that aren't like you're pretty sure that you're going to get a slight performance increase at the very end, but they're engineering steps, they're time consuming, and you can squeeze that last bit of performance out, but you should definitely go through the first steps to begin with. And so if you're going to solo, you should climb smaller mountains. If you look at climbers, they get really used to their gear. They know how their shoe works, they know how these things that clip in to the wall works. If you're going to start to train neural networks, you should really understand your gear, right? This is backprop. That's like one of your fundamental components. You should run backprop with just a single iteration and make sure that your loss does what you think it should. So you form a hypothesis beforehand, you run the experiment, you can calculate out what you think the loss should be when you just do initialization. You should get a simplified baseline, and you should make sure that you can really overfit. And so in some of the images that we've done, we'll have labels. And so kind of all your data, you'll have labels somewhere in there. And what you could do to make a very simplified baseline is you could take your output, and you can mix your label in there. And you can do that in ever harder and harder ways. If you're doing images, you can just put a little bit of a trace over the image, or you could put a big trace over the image. and see if it still trains. This makes a very simplified baseline that you can come out. And so in this, be very keyed in on how, on a hypothesis that you can pull out, that you can then test with your neural network. If you're going to solo LCAP, you should really study the routes from the ground. You should look at what others have done, and if you're going to be an entrepreneur and you're relying on this model, a big question before you start is if you can make it to the top. Like, is this actually a number that you should then go through the steps 3, 4, 5 to get to? So there's some other questions you can ask about that. When you're training neural networks, you should really just study your data for an extended period of time before you pick up the rest of the tools. Oftentimes, I'll take the data and I'll flip through images for hours. I'll go in and I'll label a batch myself. I'll go see and make sure, and what I'm often keying in on is something that my mind is doing. Like, am I able to pick up how I would detect things in these images? How much does it matter of the bigger receptive fields or the smaller blocks? How much is it color cues that I'm picking up on? Are there kind of biases or shifts? Are there two classes of data that I'm really trying to distinguish? What comes out on the tails? And I'll do all of this before picking up any of the training tools so that I can really, really understand the data that I'm going to be working with beforehand. Then you move to the mountain, you start to climb, you start to move around, you start to see how accurate the routes are compared to what you thought. How does your body work on those routes? You're visualizing every detail, and you're making sure that your mental model is correct with how you climb. And so next step for training neural networks is to go through and have this simple baseline, come back, make sure that it's working for you, go in and initialize as well as possible. And so we often see these loss curves that just go like, they start really high, they start with a terrible loss, and then they just drop right away. And what you can do is you could go in if you know that your output is going to have a certain bias to it. You can just pre-compute that. You can have that be your initial output. You don't have to go in and have it learn all of those weights. You can start from a much better initialization there. You can test on your training data. This is going to be the best case that you can expect for your model to ever get. And when you're going through and you're benchmarking, can I get a very high performance model? Being able to go through and test on your training data will give you kind of your highest level accuracy. Increase the precision of your model, use extended precision, and all of this on much more test examples than you would regularly use. Use Atom as your optimizer also. So if you're going to climb, don't be a hero. You're learning with gear here, right? You could fall off the mountain. Wear a helmet, use a belay device, keep all of this stuff intact. Think very carefully if you actually want to go and free solo this mountain. There's one slide here. If you're going to train neural networks here, there's a couple big steps that you'd want to keep. You want to make sure that you're caching the models correctly. And so you look at oftentimes there's like a guaranteed way. I found there's a lot of fanciness that people put in on the math side to how to get better models, how to understand bias and variance and things like this, how to use GANs for data augmentation and stuff like that. What I found is if you really want to get better models, get more training data, figure out the augmentations that work. Don't take those and don't put those in at the very beginning. Keep those till the end. You have many tricks out there that you can use. You don't have to start with all of them in there. Some of them are just very nice engineering ones that you can toss in at a much later stage. Image augmentation, for one example, is one where you go through and it's like simulation, but it's just much better. You start with the world as it is. You start with one of these images as it is, and then you augment in several different ways. And if you start to look through your data and you start with the step of just analyzing it in depth, you really start to understand how you can go through and you can augment this data in ways that is actually meaningful. And then you'll come to the question of you're going to put in some parameter for how much augmentation to have. And so say you take an image and you're adding in white noise to it. So like pixels, for example, on a camera are all susceptible to a certain amount of noise. And so you're going to, you have a thought, okay, I'm going to go and I'm going to augment all these pixels with noise. So now you have to choose what sort of variance you want to add. And you want to add a bias to it, and what sort of results are going to give you the best ones. And at that point, you come back, and this isn't till we're like, one step away from free soloing El Cap here, right? This is very far along in the process. This is when you're starting to get to that squeeze and tune portion, but you'll come back, and you know that your gear works. You know backprop works exactly how you want. You know that your loss, you've got the initialization, so you don't get this crazy hockey stick loss at the very beginning. It starts kind of, and you've done as good a job as you can to start it out low. You know that you're not having any sort of kind of other mismatch coming in. But then you'll come and you'll take a step like augmentation, and you'll be making this decision about where your parameter, how much variance you want on it. And so you'll go through and you'll do this step by step of you'll run an experiment, you'll run it across, you'll have a hypothesis at the beginning. You'll say, yeah, if I tune this too high, I'm going to get images that are totally blown out in both directions, and that's going to obviously be bad. If I have this number be very small, like 0, well, that's where I'm at now. So there's some number in between these two that I need to go through and choose. And then you'll run that experiment. You'll run through different parameters of it. You'll make a hypothesis beforehand, and you'll make sure that it tunes just how you think it would, right? There should be some sort of graph that it gets better. It kind of peaks out, and then it gets worse. And if you see that it does something different, that's a problem. And when you're really trying to get to that peak performance, because the only reason that we're running neural networks is because we want an ever-increasing performance. And so you need, in this case, you'll find this little small failure there, and you have to come back and, hopefully you haven't gone through and ran, and tossed in 10 things at once. That's one of the very worst things that you can do, is go through and toss 10 things in at the same time and then expect them all to kind of magically sit nice at the end. And it's one where, when I go through and I build these systems, you're doing it over a long time. You're building a system to go out and have max performance. And that's a big part of also when you take it and ship it into the world, is that you'll always come back and you'll be retuning these parameters kind of for the life of the system. And if you've gone through and you've understood each individual component, then you'll be in just a much better place. When you come and you're ready to free solo El Cap, don't be a hero. Only move to here if you want to have state of the art. When you're really sure and you're ready to kind of tune and squeeze at the very end, don't use grid search, use random search. Ensemble methods are very good. It's always going to take more compute there. Start to get into extreme amounts of data, and I think one of the best bets people can make is on compute. Anybody who bets against compute almost always loses. And so, come back to kind of a question at the beginning. If you go in and you start to question each one of these aspects of how true is it in this world where if we take hail hit cotton and we now include this as part of our training set, does our model actually generalize to it? And it's true like some of, it's not true 100% and it's not true 0. What we found is that with deep learning and these sorts of tools, it tends towards to be much more true than false. It tends towards not having to require all these new parameters to be re-optimized, right? You don't have to maybe go in and re-optimize your 10 different steps of data augmentation for it, but it doesn't always turn out to be 100% true. In robotic systems, we found that, and this was really not obvious when starting out. And so you could take each one of these as a single day's test. So we went to the field 4 times. We collected data, 4 different data sets, 0, 1, 2, 3. And we were looking for how we should do our train test split. So naturally, take your favorite percentages, 80-20, 80-10-10, 70-15-15, whatever it is, and split up training data from test data. And then go through, train actually on your training data and see how well you do on your test data. And this was a major problem. We would get really good results on this, and then we would go to the field and we would get terrible results. And then we would come back and we would have collected another one, and we would be working on it, and we would label it, of course, and then we would put it in here, and then we would do good again. And can anybody see why this is a problem?
You haven't seen the future, so you're training on 1 hour of the next day.
Yes.
You don't know the next day.
Yeah. So this was a major problem because inadvertently we were cheating. This is not fully training on your test set, but this isn't keeping them separate. And so you have some of that next day's data in with your training data. And so for robotic systems, we moved to one where we'll do single holdouts. We'll take it an entire day, an entire field, an entire batch, and we'll hold it out completely. We'll then round robin this in between, and that will give us many different data points. And so instead of just having kind of single instances of how we're doing, this is a super old graph, but we would take all of these different data points and we'd plot them, and what would happen is if you're down here, you get a phone call and the machine is broken. And this graph in particular was back in the days of kind of pre-deep learning, and so then I would go into the office and I would have to feature engineer all the numbers to be up and to the right again. And then you'd kind of move from there. But in robotic systems, if you start to do this round robin style, you can come through and you can make and you can plot each individual point. Like your big goal is take the worst point and move it up. Take the worst point and move it up. It's not about moving the average. It's not about moving the center. The ones down here are your bad days. And so you start to get some different metrics we found when working with the robotic systems. One of the things we were working on was how do you make a model and how do you actually find these parameters, this entire setup, the network architecture, to go through and be as general as possible for a crop that we weren't able to collect data on. And this was kind of posed to us because we wanted to do cotton in America, and we had cotton data from Australia. We didn't actually have that yet, but we wanted, cotton data in Australia is available 6 months off cotton data in America, northern southern hemisphere. And so we went out and we challenged ourselves to be able to make a model that would generalize to every individual crop. And so if you could go through, and the thought was, if you can tune all of these parameters and you can get everything set up to generalize in between corn and chickpeas and in between peppers and lettuce, then the very same thing will work if you wanted to generalize in between cotton in Australia and cotton in the United States. And that way, we would have had all of these building blocks set up kind of as good as we could, so that when we started to get cotton data from the United States, so our plan was, right, the crops are seasonal, we'll go down and we'll collect cotton data in the United States, and we'll take it, we'll spin a model over the next couple days, we'll deploy it to the field, and we'll see how it works. And then we'll take data, we'll deploy it to the field, and we'll see how it works. But it was with a data set that we had no prior knowledge of. Right? We had no data from cotton in Texas at any point. And so we worked really hard to build all of these blocks, to kind of use this example of having a model and the hyperparameters and the augmentation and everything in place to be able to generalize in between each one of these classes so that when we came to a new class, we could go through and we could use all those mechanisms. It's kind of a big pre-training step for us. Here's some examples of some of the images that come in. Here's some examples. I just pulled these from our Slack channel quite a while ago, but of several challenges that having this bot deployed in the world gives us. Gives us tons of weeds coming in, very hard to detect plants, oversaturation in many cases. Who knows even what to do with the top left. When building and deploying the product, you'd have to come, right? And when you dig into your data set, you may find stuff like that. You're just like, does that even fit inside my class? Should I go through and remove it? Is this some other pre-step that I do? One of the things we've found is that as we scale out these systems, you'll start with like the vision system that I've talked about the most is this one where it takes like an image of, it does this, right? It takes an image, and it goes through and it detects cotton and it detects weeds, or it detects lettuce and detects weeds, or something like that, right? But at the same point, that's just actually a pretty small number of the vision systems on board. To really build out these systems, found is kind of every time you want to kind of exponentiate the number of machines that you're doing, you have to build twice as many systems. And so as we've scaled out, You go through and you build systems that may detect things like this, and it may detect smudges on the lenses, and it may detect all of these things so that you can easily take that data and then move it into the side bucket. It's no longer stuff that your machine learning algorithm has to fight with. It's now stuff that somebody with a rag can go through and wipe off a lens or something of that nature. I've often set up teams, and we set them up in 3 different groups. One of the big reasons to do this is that found that these problems are kind of so hard that you really have to have a full stack person all the way through. But where you can have nice boundaries in between people and nice roles and responsibilities, you should take advantage of that. And so we have a data labeling group, and they take requirements from the machine learning experts and the product managers for what data to put in place. The machine learning experts are responsible for the magic to happen to create the algorithms. The product managers actually get to decide what data they want to work with as part of their validation tests. And so in this split, you don't necessarily have the machine learning engineers say that. It's the product managers that are going through. We've done a lot of training and working with individual product managers to have them be able to talk to machine learning experts where they can give out precision and recall, and they can talk in the language and nomenclature and actually specify products in a useful way. And so I wanted to quote one of the sources from Andre's blog, and thank you, and open it up for questions.
Can you describe in more detail the bias initialization? What techniques you use there?
Yeah, so in initialization, you can go through and you can look at the kind of the last layer output. And so if you knew that one of your classes was weighted like say it was 5-to-1, you can go through and you can initialize one of those classes in a 5-to-1 weighting. There, you can also go through and yeah, that would be the big first one. You can also look at losses, right, with just random initialization. So pre-training almost never hurts on a network. If you can go in, this isn't like the unsupervised training world. This is supervised pre-training of a network. And supervised pre-training is just a great way to go in and initialize your networks. And so when you start to get things like batch norm and dropout and mainly batch norm in place, having this good initialization at the beginning helps some of those parameters.
I thought there was something other than, so it's just you train a model, you start with that for the next one you train,
Yeah.
like when you transfer.
Yeah.
Okay.
How did you get through how do you get through convincing people who use the product of the magic behind the product and deal with the mistakes that the model might make?
How do you convince people with
Yeah, like if you walk up to someone and if you haven't heard of a machine learning system like this feels like black magic.
Yep.
How do you get people to buy into that? And
Yeah.
then it's also going to be not 100%, so it's going to make mistakes.
Yes.
And how do you deal with that aspect of the product?
Yeah. I think you might have, depending on who your audience is. So there's a group of people that have an algorithm in place already, and they're just looking for one that has a better performance. And so that group is one where it's kind of an obvious, hey, yeah, you like 93%, how about 95%, right? And so you can get an easy sell into that, depending on the data pipeline set up around it. When you go in and you start to talk about a totally new application, right? Like we've seen numerous, especially in the perception world, numerous opportunities open up that just did not exist before. Because you see models, you know, in like, you look at ImageNet in 2011 and it's like 30-some% error, right? That's not a, like, I was looking at that and I'm like, okay, you know, that's not good enough for many things. And so, you know, then you may be convincing, you know, first you have to convince yourself, like, is this model actually going to move up to the percent where it does make sense to then launch it in this application? And then you get into some of the specific product side of it. You know, what, you know, sometimes pretty costly to bring some of this stuff up. There's a lot of infrastructure involved. Is it going to be worth the investment for, on the people side to bring this stuff up?
So how did you go through the process of retrofitting your organization or the whole engineering pipeline from machine learning to deep learning? Where did all those future engineers go? And, you know,
Yeah. Yeah, so we kept all of the feature engineers. They all became deep learning engineers. Including myself. I mean, this is like so there were some like wild days. So if you look at, like you had the AlexNet paper and you had this VGGNet for a while, and kind of things pre-ResNet. I would not say that these systems acted in ways that you would expect them to act. Like you would go through and you would do stuff with it and it would act in totally unintuitive ways. You know, you would go in and you would add a layer and it would get better performance, and then you would add a layer and it would get worse. And you would add another layer and it would get worse. And you would add another, and you'd be like, what's going on here? And so people at that time, you know, in like deep learning, it was like the nomenclature was more than 7 layers, right? Now it's kind of synonymous with neural networks. But at that time it was like, yeah, if you got more than 7 layers to train, you were doing deep learning. And it was because it wasn't figured out necessarily how to get more than 7 layers to train. And so, like some of the VGG work, right? It was like you'd go through and you'd train a network. You'd take all of those weights and you'd transfer it to a slightly deeper network, and you would train it a little bit more. You'd do the exact same thing again, and you train it a little bit more. And that was your entire pipeline, because it did weird things of when you'd add a layer, it would get worse, and you'd add a layer, it would get worse. So this comes back like some to kind of figuring out the specific details. I forgot what the actual question was here.
so like how did you retrofit your engineering pipeline from
Oh.
machine learning to deep learning?
Yeah, I mean we did it in a big leap. So we decided to make an entirely different product than we were making before, because I went through and I looked at the numbers, and the numbers were better. And the numbers actually justified a weeding product in the market, and I thought that we could hit higher numbers. And so we went from lattice thinning that was running on quad-core desktop i7s to starting to pull and get pre-orders on NVIDIA Jetsons that came out, and we bought, you know, racks of GPUs and started doing training. This was when Caffe was kind of the only thing around, and you know, we were just slowly building up our knowledge in this area. We started out by taking some some of the lattice data and just seeing if we could do very basic things. And so in images, you'll get to a point where you'll want to go through and you'll want to put boxes around, or you'll want to do semantic segmentation. These are challenging tasks. These are like on the, you know, far end of the scale. What we started with was classification. So can we pull out just a patch that we know is perfectly lattice, because we knew where they were at, and a patch that is something else? And can we label these as far as classification goes. We started to build that confidence in, the thought was, if you can't do classification, you can't do detection. If you can't get classification rates to be high, you can't get detection rates to be high. And so we were going through and benchmarking time by time, how accurate can you get it? Can you get it to the product stage?
Probably just one or two more questions.
So to back to his question, right? The feature engineers in the machine learning era, right? I mean, can they be better in understanding the deep learning models because they have a domain knowledge, so whether the model is correct or not, or whether it's whether it's using the right kind of features to kind of make predictions in the deep learning world also. So what I was trying to say here was that the feature engineers in the machine learning era, right? Can they be used to kind of interpret the deep learning models because they have a domain knowledge, because they were doing feature engineering before, right? So
Yeah, I mean, we, just us as a team, we went through, and it was also at a time where it was essentially impossible to hire deep learning engineers on a very small startup salary. And so we decided to do lots of internal training. So the people that were that were part of the computer vision team before, that were doing feature engineering, we put on a track where they would take classes. They had 30 to 50% of their days set aside to learn, to experiment with these different models, and we built a little community. And there's not like, it wasn't like there was lots of us there, right? There was 30 people in the whole company at the same time, so we're talking like 4 people. Went through and did this, and but yeah, that was to go through and to have our own community inside of the company that we could pass off papers and we could learn and we could implement stuff. It was a big switch to switch the hardware that we were using, to switch the training methods that we were using. It became so much simpler from a systems architecture point of view. One of the things that's very nice about a ConvNet all the way through, that's not obvious in a robotic system, is it takes the same amount of time to do inference every single time. All these classical computer vision models that would go through and it would find individual features, and it would pull those out, and then you would have a list of key points, and then you'd pull out features, and then you'd classify those. Well, your list could be, this long, or it could be this long, at which point it's going to take this much time versus this much time. And in this robotic system, you're running in this world where you need it to fit in a time bucket. And so even though the compute requirements for deep learning were much higher, they were much more predictable. And we didn't have to go and deal with kind of this systems lag that came in and sat on top of, that we'd like, the computer vision engineers would pass off a model that would, sometimes take 20 milliseconds, but every now and then take 5 seconds.
Maybe last question. Yeah. How do you simulate the real life issues, like you mentioned, like smudges in the camera, or maybe a rainy day, or how do you anticipate for all that and train your models?
Yeah, we would go through and we'd actually collect data. Many of these, like smudges on the camera, are not deep learning based models. They're ones where you'd look at a couple images in a row and you'd kind of hand tune a feature out. And so we'd go through and you'd pick out these side objects. You'd pick out the ones and you'd say, here's one with a bunch of hay in it. Let's not count that. Here's one with undersaturation or oversaturation. We're dealing with cameras outdoors, so that's a big problem. And so we'd be able to go through and segment those individual ones and have individual team members work on those problems. One of the funny ones actually with, we were using in the machine learning days with feature engineering, went through and we collected a lot of fields worth of data. And this is one about like a non-intuitive thing. So we would go and we would take, and we had 10 fields, we had 15 fields, we had 20 fields, so on and so on. And we found that the model would get better. This was a support vector machine, so it had, we tuned the kernel like crazy to get that thing to work. And it worked better up until 19 fields, at which point you'd add the 20th in, it wouldn't get any better, 21st, no better, like all the way through 100. You'd pretty much be flatlined. And it was at that point, like that model, the support vector machine, didn't have enough capacity. Right? It had like 150 different values that it was learning. And it was one of, and we were sitting there for about 6 months, which felt like forever, with this model and this extra data that came out. And knowing that we were, collecting more data and we weren't kind of fulfilling this virtuous cycle of having more data, having more labeled data, and having a better model. It's something like in the deep learning, like you'll never run. Nobody's ever going to run into that here, right? Add another layer. And so, yeah.
Great. Thank you, Lee.
Well,